And welcome back. I think I lied to you last time and said the last one was the last of the chemistry review videos, but this is the last one. And last time we ended up talking, ended at the very end with a chemical bond, with the idea that it's when atoms share or transfer electrons in order to complete their outer valence shell. So the first one we'll take a look at today is going to be the covalent bond, which literally means the sharing of valence electrons, so covalent. So we've got the sharing of valence electrons, and a great example of this is going to be methane, CH4. And as you can see in the diagram that I have up here already, carbon has 4 valence electrons, shown in the red, and hydrogen has 1 each. And if you remember, we said how many bonds does hydrogen like to form? 1, because it has a valence of 1. How about carbon? Carbon likes to form 4 bonds because it has a valence of 4. So in this case, each hydrogen, as shown here, each hydrogen will share 1 electron with carbon. And what happens is carbon reaches its octet, so now we have 2, 4, 6, 8. The hydrogen only wants 2 because it's a smaller atom. Each hydrogen has 2. And so if the electrons are shared equally like they are in this case, it's nonpolar covalent. Now up in the right here, you'll see that there's the En. The En stands for electronegativity. And it's a measure of an atom's ability to attract shared electrons. And in this case, carbon has an electronegativity of 2.2 and hydrogen 2.0. So there's a difference of 0.2, which is negligible. So in this case, the 2 atoms, carbon and hydrogen, are actually sharing those electrons equally, and we get what's called a non-polar covalent bond. Okay. Now, what happens if they're not shared equally? Whoops, I'm getting ahead of myself just a little bit. So here's an example using the Lewis dot structures of how the covalent bonds can be formed. So if you look at the very top, we've got hydrogen, each has 1 valence electron. They would like 2 in order to complete their outer shell, so they will share. And anytime we have a shared pair of electrons, it can be represented by a dash, which is a bond. Just remember that each dash represents 2 electrons that are being shared. So here's an example of chlorine, which has a valence of what? If we count the dots, 1, 2, 3, 4, 5, 6, 7. Each chlorine has 7. They would like 8. So what will happen is they will share a pair, and again, that's shown as a dash, and a covalent bond that represents 2 electrons. Okay, and what happens if we have 2 different atoms? In this case, hydrogen and chlorine. Well, hydrogen has its 1 valence electron. Chlorine has its 7. Hydrogen would like to gain 1, so would chlorine. So they share, and we form that 1 bond between them. So we can look at the bonding pair of electrons, but there are also what they call lone pairs. So chlorine has 3 lone pairs of electrons that are paired together but are unbonded. So this is how we show the covalent bonds with a Lewis dot structure. So now what happens if they're not shared equally? And water is the classic example that we're going to use for this. So what happens if they're not shared equally? We get what's called a polar covalent bond. So the electrons are not equally shared, and what it does is it creates regions of partial negative and partial positive. So this little squiggly symbol here means partial. And when we look at the bond that forms between oxygen and hydrogen, oxygen is what we call an electron hog. It's highly electronegative. So even though it looks like it's going to share electrons right down here with hydrogen and right here with the second hydrogen, they're not equally shared. The oxygen pulls the electrons towards it, and it becomes partially negative. If the oxygen becomes partially negative with the electrons around it more often, that leaves the hydrogens to become partially positive. When that happens, we get a polar moment, and this bond now becomes polar because there is a separation of charges. We've got an area that is partially negative, and we also have an area that is partially positive. So that's what creates a polar molecule. And if you look over here on the right, you can see if 2 polar molecules are in the same vicinity as each other, the negative oxygen of one will be attracted to the positive hydrogen of another, and we form a hydrogen bond, which we'll talk about shortly. So this idea of electronegativity is the ability to attract shared electrons. And the two ones that you've got to be familiar with are oxygen and nitrogen. So in terms of biological systems and for AP Bio, oxygen and nitrogen are the two ones that you've got to remember have a high electronegativity and are likely to form polar covalent bonds. Okay, so here's an example of water, and the red outline is showing kind of the electron cloud, where oxygen has its lone pairs and hydrogen has the shared pairs. But hydrogen with its electronegativity of 2.0 and oxygen has an electronegativity of 3.1, so we have a difference of 1.1. That creates enough of a difference that there is a polar moment and we get a separation of charges, and that creates the polar molecule. Okay? Now let's look what happens when electrons are physically transferred. So when they're shared, we have a covalent, and on the continuum, we can go all the way over to where they're actually transferred, and we get what's called an ionic bond because it forms ions. So here electrons are transferred, so we have cations, the positive, and the anions, the negative charge, that attract each other. So in the case of sodium, sodium has its one valence electron that it really doesn't have any interest in keeping, because if it removes it, it has an octet underneath. And chlorine has 7 valence electrons. It would really like to gain one, so there is a transfer from sodium to chlorine. And what that creates is it creates a positive sodium ion, because it has the same number of protons but one less electrons, and a negative chlorine ion or chloride ion that has the same number of protons but one extra electron. And then, because of the electrostatic attraction between the positive and negative, they are attracted to each other and they form an ionic bond, and that gives us salt. So again, looking at it with the Lewis dot structures, the one that I just showed you before, here's sodium and chlorine, and again, if we look, sodium is more than happy to give up that one electron. Chlorine is more than happy to accept it. So now chlorine has a complete octet, or they're calling it a closed shell. Those two will then be attracted to each other because of the opposite charges. Magnesium and oxygen will do the same thing. So magnesium has 2 valence electrons. Oxygen would like to gain an additional 2. So magnesium will give up 2 electrons and form a magnesium ion and an oxide ion. They both have complete outer shells now, but they are attracted to each other and they form magnesium oxide. How about calcium and chlorine? What if the number of electrons that one is willing to give up and one wants to receive aren't the same? Well, we have the case here. Calcium has 2 extra valence electrons that it will give up. One can be grabbed by a chloride ion. The second can be grabbed by a second chloride ion, and so we get the calcium ion and 2 chloride ions. So when we write the molecular formula of this, it's written as calcium chloride with a subscript 2, because in order to get the charges to cancel, the positively charged calcium has a +2, and each chloride ion is only -1, so we need 2 of them, excuse me, to get the molecular formula of CaCl2. And the last thing that I'm going to, excuse me, the last thing that I'll touch on briefly is a hydrogen bond. We'll spend a lot of time with this when we do our water unit. But a hydrogen bond is a weak bond in which a hydrogen atom in one molecule is attracted to an electronegative atom, usually nitrogen or oxygen, as we said before, in the same or different molecule, to bond to another species by means of hydrogen bonds. For example, water hydrogen bonds with itself. So we have the hydrogen right here, and if you remember, what's the charge on that hydrogen? It's partially positive. And it will be attracted by a hydrogen bond to the oxygen, which is partially, partially not positive, but partially negative, and that will form the hydrogen bond between those two water molecules. And as I said before, when we look at the properties of water, which is incredibly important to biological systems, we'll deal a lot more with hydrogen bonds and the properties it creates in water, like capillary action, surface tension, and such. And the last diagram that I'll leave you with is water. And in a solution, or when we have water together, each water molecule interacts with 4 other water molecules to form those hydrogen bonds. So the one in the center, the negatively charged or partially negative oxygen, right here in the middle, will be attracted to 2 different hydrogens from 2 different water molecules. The hydrogens will in turn be attracted to the oxygen of 2 other water molecules. So each water molecule is attracted to 4 other water molecules, whether it's pure water or in a solution. So that wraps up the chemistry review portion of this unit. And as I said before, we'll be using these topics extensively as we go through the year in the AP Biology. So thank you for your attention, and we will see you for the next unit.